Last time we started talking about how we can go about comparing two quantitative variables. Namely, we said that we can make scatter plots and look at the scatter plots and make statements about the direction, the form, and the strength of the association. So for example, what we have here I would characterize as a relatively strong negative linear association between the gas bill and temperature. Cool. So what we're doing today is talking about what exactly we can say about some sort of association like this. Namely, what we want to do is come up with some sort of model, some sort of explanation for what this relationship looks like. And what I mean by that is we want a line that describes what's going on. Now, we'll talk a little bit in a minute about what exactly we want in this line, but this doesn't have to be an exact estimation. What we're talking about is a model that does a reasonably good job of explaining what's going on. So our goal is that we want to find an equation for a line that describes this. So rather than writing y equals mx plus b, which hopefully everyone's familiar with as a form for standardizing how we can write an equation for a line, we're going to use a slightly different convention. So rather than this, we're going to say, all right, y equals b naught plus b1x. And changing these to b's is just the convention that we're going to use, because at some point we might want to add more explanatory variables. And rather than having to go through the alphabet and use M, N, O, P, and use a bunch of different letters, we're just going to start using subscripts. But the idea is the same. We're looking for an equation of a line. The other sort of slight change that we're going to make is that rather than y, we're going to call this y hat. So this symbol here, the caret symbol, when above some variable, is pronounced y hat. And I always sort of mentioned that back in when I was doing undergrad, the physics department often has like some sort of t-shirt that's like their physics department t-shirt for the year. That year they had hats, and on the front of it was this, which of course is pronounced a hat. And yeah, we all got a kick out of that. Anyway, what we're trying to get here is we want an equation for a line. We want an equation for the line that does as good of a job as possible of describing this association. In other words, the line that often is the one that visually makes the most sense for describing this association. So before we jump into how exactly we can calculate this, I want to first think about what exactly we're looking for, right? So if we have, let's draw two competing lines here. So we've got this line, which I think looks pretty good, and let's say we also have this line. All right, so what makes the first line better than the second line? And like, obviously we can look at it and say, oh yeah, the green one's just doing better, but what exactly do we mean by that? And there's a couple ways of actually quantifying this, but the features that I want to focus on are two features. So I would like my regression line to go through the middle. So one of our goals is that we want to find an equation for a line. An equation for the line that includes the middle. And what exactly do I mean by the middle? It's like, well, maybe because temperature is, let's say, going from 0 degrees to 90 degrees, this is just a distribution. We can find the average temperature. Similarly, the gas bill goes from $10 to, let's say, $200. We can find the average gas bill. So when I say that I want the equation, or I want the linear model to include the middle, what I really mean is if I took the means of each of the two distributions by themselves, I want it to include that point, the mean point. So I'm going to replace this. Cool. Okay, so that's one attribute. Well, I could draw another line. Let's draw this line. So this pink line is, just like the green line, also goes through the mean point. And now the question is, all right, what makes this first line better than our new line? And, well, it just does a better job of getting close to the data points. What I mean by that is this line, or this portion of the line, is further from the data set than our first line. Okay. To put that into words, a goal of our model, a goal of our line, is to be as close as possible to as many points as possible. And it's worth pointing out that our best line might not actually exactly hit any of the points, right? We got pretty close here and here, but we're still probably a little bit off. And that's okay. We're not asking our model to be exact on any of them. The goal is just sort of on the big picture. We want to be as close as possible. We want to make this last idea a little bit more rigorous, a little bit more numerical. And in order to do that, we're going to talk about what's called the residuals. So the general idea is that for each point, we're going to measure how far away from the line the point is. So the definition is going to be that the residual, which we're going to denote typically with an E for error, for an individual point, so E1, E2, etc., is going to be the Y value minus the predicted value. In other words, for this point, its residual is going to be its Y value minus the predicted value for that given X value. So we're talking about this distance. This is Y, let's call it the sixth point, let's call it Y6, and this is the predicted value of that point. So then the residual is going to be the difference between these two, or Y6 minus Y hat. So we can do this. We can calculate the residual for each of the points. And a goal is to minimize the residuals. We're trying to come up with a criterion for our line, for our model, that reflects the idea that we want to be as close to the points as possible. And one idea would be, all right, for each candidate line, we're going to calculate the residuals, and we want the line that minimizes the sum of the residuals. Sounds reasonable. One problem with that is that, okay, so we have our green line here. If we have a parallel line that is is relatively close to it, this is actually going to do exactly as well at minimizing the total residual, or the absolute values of the residuals. And clearly the green line, this first line, does better than this new line. So we want to come up with some sort of slightly different criterion to reflect the idea that we want to be as close as possible to the points. So instead of minimizing the total sums of the absolute values of the residuals, we're instead going to square them. So our goal is going to be as close to the points as possible, aka we want to minimize the sum of the squares of the residuals. All right, so why is this squared? Why do we choose to square these residuals? Well, like a lot of things in statistics, it's a somewhat arbitrary choice. By having a higher power here, we are more heavily penalizing points that are particularly far away. So we could have said that, all right, well, let's cube these residuals. But then that's going to really heavily penalize points that are, for example, way out here. So it's a balance of simultaneously trying to minimize the really big residuals and minimizing a bunch of slightly bigger, small residuals. Anyway, that's not too terribly important. The general idea is that we're using the squares of the residuals as our measure for how good a line is, because it strikes a good balance as far as giving us a line that we think does a good job of explaining the data. Cool. Okay, so we often call this line the least squares regression line, because it's going to be the model, it's going to be the line that minimizes these squares. So in the future, I'll probably often call it the least squares regression line. This is why, because what it does is it minimizes the squares of the residuals. There's one last thing that we need to check before we actually calculate one of these, and that's that we need to make sure that our data set is actually conducive to a linear model. So there are 3 assumptions that we're going to check. The first is just a sanity check. Let's make sure that we're comparing a quantitative variable on both axes. These linear models don't make sense if what we're talking about are categorical variables, because we need to talk about distances between them, and it doesn't make much sense to talk about how different vanilla is from strawberry as opposed to from chocolate, right? It doesn't make sense to talk about measurements in that sense. So we're sticking to quantitative variables because it doesn't make sense to compare the distance between 0 degrees and 10 degrees versus 60 degrees and 90 degrees. Anyway, so we want to check to make sure that we have quantitative variables. We want to check to make sure that our distribution is roughly linear. So the book uses the term linear enough, and the idea is that we don't want to be applying these techniques if our distribution obviously looks curved. Now, how exactly we can tell if maybe it's close, we'll get to in a little bit. But for now, this first step is really, let's just look at the plot and tell, does it appear to be linear? The third condition is that we want to avoid outliers. As we saw in the discussion on Friday, it's possible for a single point to pretty drastically change things like the correlation coefficient. And as we'll see in a second, that's actually a pretty key piece in finding the equations for these regression lines. Okay, so once we've checked these 3 conditions, we can then move on to saying, all right, let's actually calculate the equation for a regression line. As I said earlier, one way to find an equation for a line is to identify a point and a slope. And we said that we want our line, we want an equation for this line to include the middle of our distribution. In other words, we would like to include that mean point. So the point that we're after, or the point that we can use for our equation, is the mean point. So x bar is the mean of the x, or explanatory variable. Y bar is the mean of the response variable. And then the slope is going to come from that correlation coefficient. So if you'll recall from last class, with this correlation coefficient, R, if R is positive, then the association is a positive association. We've got a positive slope. Negative R, negative slope. So we're going to use our correlation coefficient as a piece of this, but the slope should pay attention to the units. We've talked a lot about using the standard deviation as a unit of measurement. This is one place where that comes in. So we're going to use the standard deviation for the y variable as a measure for rise, and the standard deviation for the x variable as a measure for run. So the slope that we're after is going to be the standard deviation of the response variable over the standard deviation of the explanatory variable. Cool. So with these things, with all these components, so there's a few things we have to calculate. We need the mean and standard deviation for both variables, and we need the correlation coefficient. Once we have these, it just becomes an algebra question. Given a point and a slope, what's the equation of the line? If you'll recall from high school algebra, if we have this point and a slope, we can find, using the point-slope form, the equation of the line. So if we just plug these things in, we can see that y hat minus y bar, so y is the function, we're calling the function y hat, y bar is the y is one of our y values. So y hat minus y bar is the slope, which we're going to call b1, x minus x bar. And doing a little bit of rearranging, we can see that y hat is y bar minus b1 x bar plus b1x. So this piece are all constants. So this thing is just b naught. So when we say that the equation that we're looking for is y hat is b naught plus b1x, we can specify b naught and b1 values by saying b1 is our standard deviation of y over standard deviation of x, and b naught is y bar minus b1 x bar. So collectively, this piece and this piece specify the equation of the least squares regression line. All right, so what we're going to do is plot these actual residual values. So for our first point, we want to know what is this distance. And this particular data set, I'm just estimating everything. I might say that that distance is, let's say, 10. So the first point is a distance of 10 below the model line. Second one's maybe a little bit more. So this point corresponds to that point. It's the same x temperature value. And then doing a few more, that third point is somewhere up here. This one's kind of low, right next to one that's fairly negative, and so forth. So we can fill out the rest of this residual plot where what the thing that the y-axis that we're plotting is this difference in actual value and the predicted value. Okay, so it's important to note that the units, so the scale on this y-axis is shrunk a little bit, but it still is gas bill in dollars. So the residual is still measured in dollars. Okay. There are a few reasons that we would like to look at the residual plot. And one of them is to check to see if this plot originally did follow a linear association. Sometimes if we have a plot that is slightly curved, we can't really notice it as it is, but if we instead plot the residuals, we might notice some sort of pattern. So if instead of this, we had a residual plot that looked more like this, then this would be an indication that our data set maybe wasn't a straight line to begin with. If there is some sort of pattern, so in this case I'd say that it looks sort of U-shaped, it's typically easier to spot with a residual plot. Another reason that we're talking about residuals right now is that by looking at the residual graph, we can appreciate how good of a model our linear regression line is. Namely, we're going to compare the standard deviation, or more generally the variance, of the residual distribution versus that of the gas bill distribution, or of the original response variable distribution. So notice that originally our values were ranging from 10 to 200. So a rough estimate might be that the standard deviation is something in the ballpark of, let's say, 50. Whereas down here, because our residuals are ranging from, let's say, -40 up to 30, it might be reasonable to say that the standard deviation is something closer to 20. So let's go ahead and estimate the standard deviation down here to be about 20. We've spent a while on how R is a measure of how close to linear a distribution is. Well, as it turns out, R, or more specifically R squared, is also a measure of how much of the variance of the distribution is accounted for by the model. In other words, how much does these standard deviations decrease? So numerically, and this formula is not important, but if we found the standard deviation of the residuals divided by the standard deviation of the y values, then this is going to end up being equal to 1 minus r squared. In other words, if we have a large r, as in something close to 1, this number is close to 0, and this fraction is very small. In other words, there's very little bit of variance left over in the residual plot. In our example, since the standard deviations dropped from 20 to 50, the r value should, if you ended up solving this for r, I believe you get something like 0.916. So this is saying that, hey, this is a pretty good model. This is a pretty strong association, and that's reflected not only in these appearing close to each other, but by the fact that the residuals are small, which really is sort of just two different ways of saying the same thing. But this r squared, or r, is a measure of how good of a model a linear regression line is. All right, the last thing that we're going to talk about in this video is, once we have one of these models, how do we interpret it? Once we have an equation for the least squares regression line, what do we say about it? How do we use that information? So let's take our example from before. We are comparing the gas bill in dollars to the outside ambient temperature. And let's say that we went through that process and we found the correlation coefficient, we found the means, and we determined that the equation of this line was y hat equals, let's say, $210 minus, let's say, $2 per degree Fahrenheit. All right, so it's important to pay attention to the units here, because that's going to give us clues as to how we can actually use this information. So this part, when we say this minus $2 per degree Fahrenheit, means that the model is indicating that on average, we would expect our gas bill to be $2 cheaper for each increase in degree Fahrenheit. So whenever making one of these sort of statements, it's really important that we don't imply that this is a hard and fast rule. We don't think that if it gets 3 degrees warmer, we expect our gas bill to be exactly $6 cheaper. We always want to use some sort of wiggle words that make it so that the statement that we're making reflects the idea that this is a model, this is an approximation, and none of these are exact values, but this gives us a rough sense of how does the, in this case, gas bill respond to changes in the temperature. The other main way that we can use this model to make some sort of statement is by predicting some value. In other words, if I were to say, if it was, let's say, 60 degrees out on average this month, what do I expect the gas bill to be? So obviously, a lot of things go into what exactly the gas bill is going to be, and there's a lot of variance to this whole system. But the question is, given the information that we have, given this model, if the temperature is about 60 degrees, then the model is saying that we would expect the bill to be, let's say, about 90 degrees. Right? And again, we don't want to say that the gas bill will be $90. What we really mean is that we expect the gas bill to be approximately $90. Anything sort of in this range is entirely reasonable. This is just saying that, hey, maybe if the bill now was $200, that would be surprising. So this is, again, a rough idea. The model is giving us a rough sense of where we expect some new value to lie. So we want to make sure that any statement that we make reflects that fact that we're not exact about any of this. As I've said a couple times, learning the steps in solving one of these things, in this case, finding the equation of the least squares regression line, is far much less about you having the tools in order to find one of these things by hand, and more about getting a sense of what the moving pieces are, what all goes into finding this equation. So in the next video, we will talk a little bit about how we can ask R to do most of this for us, but I still want to take our time working through some of these examples because it gives us a sense of what exactly is going on rather than just having a computer tell us a number. Next video, we'll also talk about what to do if our distribution isn't necessarily linear to start, and what to do if we have some outliers. But we will do that next time.